Okay, next up we have these two problems where we have a planet and we have to find the a spherical planet, and we have to find the gravitational field in and around it. So we're going to look at this planet, which has a radius of capital R and a total mass of m, and it's also got a density, and the density is uniform, even if I didn't quite say it in the first of these questions, but the density is rho. And so you recall that rho is, or density is mass divided by volume. So density rho here is mass divided by volume. And the volume of a sphere is 4/3 pi r cubed. So rho is going to be the mass divided by 4/3 pi and then big R cubed. So if we want to clean that up a tiny bit, we can do rho equals 3m, so we take this 3 down here and pop it up top. 3m over 4 pi r cubed. Okay. And this is going to be useful because basically we have to do this problem, once with mass and then once with rho. And so, and once with density, sorry. So, sometimes it's easier to do the density version first and then convert to mass. Sometimes it's easier to do the mass version first and convert to density. So first, what we want to find is the gravitational field, the magnitude of little g, which is the planet's gravitational field, at a point some distance r from the center of the planet. So I'm going to draw that. This little r here is some distance from the center of the planet, and it's got, at that point, there's a gravitational field. We know it points toward the center of the planet, right? And it's got a magnitude of g. So we want to find this both for when little r is greater than big R, so when you're outside the planet, and for little r less than big R when you're inside the planet, or greater than or equal to, less than or equal, but you get the idea. So for r, outside the planet, it's pretty easy because shell theorem says that any hollow shell with uniform density can be treated for gravitational purposes as a point mass at the center of the shell for anything outside the shell. So if you're here, you're outside the entire planet, and the planet we can think of as just this sort of nested set of concentric spherical shells all the way down. So that is easy to do. So what we do is we say the gravitational force is capital G, big M, little m over, over r squared. So that's on some object with a mass m, and that is equal to, and this is basically the definition of G here, is equal to mg, m little g. So what we get from that then is that quite easily big G little g, this is little g, equals big G times big M over r squared for little r that's on the surface of the planet or above. So that means that little r has to be at least big R, so greater than or equal to big R. All right, easy enough. Now, the tricky part is what happens if you are inside the planet. So, in fact, let me switch to a different color just to make this a little clearer. Use brown. Yeah, sort of lightish brown. So let's say you're inside the planet and your little r is, actually let's make it even smaller than that. Your little r is like that, and here's the point you're interested in, okay? Now, the shell theorem says if you are inside a hollow spherical shell, you feel no gravity from that shell. But if you are outside the spherical shell, you feel gravity as though you were as though it was a point mass at the center. So what we do is we basically draw a little sphere, sort of like a little mini planet, inside our big planet, and we say that because all of these shells outside, so you imagine a bunch of nested shells outside, you're inside all of these shells, right? So you don't feel any gravity from these shells. So when you're inside the planet, you essentially ignore everything above you or further out from the center than you are. So all this stuff I sort of dashed in here, you ignore when you're at this point. But all this stuff inside here, and I guess I can do that in like light blue, which is a totally realistic color. But all this stuff in here, all this light blue stuff, you do feel gravity from. So what you feel here is gravity as though you are standing on a planet with a radius of little r, And so, you know, here's your point. With a radius of little r and the same density. So, same density, but a smaller radius. So, you know, there's your, this is basically the same as the bit of the big planet that is still under you. So this is like the core of the big planet is taken out and made into its own separate planet. And the gravity on the surface is the same as it would be if you are right on the edge of the core of this planet, for example. Whatever you call, you know, defining core as anything within little r. So, so we have to find the gravitational force on the surface of this little planet, which is going to be G equals big G, and I'm going to call this M. Let's call it M. What's a symbol I can use on that? Let's call it M squiggle, okay, for the mass of the little thing, over r squared. So this planet here has mass M squiggle, okay? And we have to figure out what M squiggle is. And by the way, squiggle is the official, don't tell me it's called a tilde, it's a squiggle. Okay, so it has the same, now we know this little planet has the same density as the big one, right? So that means that if we find the volume of the little one, and we know the, well, okay, find the volume of the little one, and we have the same density as the big one, we're just going to have M squiggle, you know, over there. So this density here for, you know, the big planet, so let's say the density for the big planet, we remember, was mass over volume of the big planet. And the density for the little planet is going to be M squiggle over what I'll call V squiggle, which is the volume of the little planet. And so now, going from this, we can move forward, and we can just take out the row here. This is density and this is density, and they're the same density. So now we can say mass of the big planet over volume of the big planet, which you'll recall was 4/3 pi r cubed. Okay, and that equals M squiggle over the volume of the little planet, which is 4/3 pi times little r cubed. Now, what's nice here is that the 4/3 and pi cancel out on both sides. So if we want to find M squiggle, what we were left with, very nicely, is M squiggle equals little r cubed over big R cubed. That's little big R cubed times big M. So here we go. So now we just take that and plug in up here to find G when you're inside the big planet or on the surface of little planet. So G here equals big G, and then we do our M squiggle thing, which means we use big M in there, and then we do R cubed over R cubed, and then this is your M squiggle here, and then this is M squiggle, and then we're just over little r squared. So there you go. So, and here's our answer then. G equals big G, big M, and then you get some cancellation here, so it's just little r over big R cubed. And that applies for r less than or equal to big R. So if you're on the surface or below, then this is what applies. If you're on the surface or above, this applies. And you will notice very conveniently that if little r equals big R, that's when you're on the surface, these two match. So little r, this cancels out and just becomes m over r squared. And then here, little r becomes big R, and it's m over big R squared. So they're the same. So that works out. And then we need to do this in terms of density. So really the easiest way to do this here, the easiest way to do this is to simply, actually probably we're best off taking this. So we take instead of going with density equals mass over volume, we can do mass equals density times volume. And so then the mass of the planet is 4/3 pi big R cubed. And so if we want to recast this as a density thing, then I'll do the density version in purple. Okay, so this is for the second problem of this pair, and I'm skipping ahead, and then we're going to go back and do part B. So G for this is the first case is, and then we just substitute this in, and it's kind of annoyingly ugly, but so this is going to be big G times 4/3 pi, and then rho times big R cubed, all over little r squared, for r greater than or equal to big R. And then for the other case, which is this one, we get big G times 4/3 pi, well, hang on, sorry, 4/3 pi rho, well, yeah, and then, oh, I'm sorry, down here, my mistake here, 4/3 pi r cubed is volume, but then we should also have the rho in there, okay, to convert it to mass, so sorry about that. A little look into my ADD world. And then this is going to be a big R cubed that we're substituting in here, but it goes over this little r cubed, so actually that's just, so actually times r. So if we want to pretty this up a little, we can take this and just scoot it down a bit so it's all nice and lined up. And then that's for r less than or equal to big R. So kind of interesting, I guess, here that you get the density out that way. Anyway, that is a 4/3 pi, even though it doesn't look very 4/3-y. Okay, so the last question, let's see if we have time for this. Yeah, sure. The last question on this pair is, then what do you do when you have a planet that is spinning, it's rotating with a period of rotation t, so it's got a, a radius capital R, of course, like before, and it's rotating with period capital T, and you've got an object on the surface, and you want to know how fast it can rotate, what's the minimum t it can have before this object flies off. So the long version, well, I'll tell you what, the short version here is that the period you want is just the period of an orbit with this radius. So something could orbit at the surface, and that's, the planet obviously can't have an atmosphere for that to work, but if something could orbit at the surface, then the period of that orbit would be the answer. To explain this a little more carefully, this thing is, of course, moving in a circle because the planet is a sphere and it's rotating, so this rock on the surface here is moving in a circle, and it's got some speed, v like that. To move in a circle, it has to be accelerating towards the center, and the acceleration has to be a equals v squared over r. Now, where does that acceleration come from? Well, it comes from gravity. And so what you have to get is where the acceleration from gravity has to be great enough to keep it down on the surface. And the acceleration from gravity, in this case, is g. So what you do is literally you just take what little g is at the surface, set it equal to this, and that is when gravity is doing, is providing all the acceleration it can to keep you on the surface. And if you try to go if the planet tries to spin any faster, you'll fly off. So big G m over r squared, this is gravity when you're on the surface, where little r equals big R, equals v squared over r, which then means, let's bring this down here, and I'll do this in blue just for fun, which means cancel these two, so cancel, which means v squared equals g big M over big R. And I think you guys can see, I want to cut this short because I don't want this to go on too long, and I'm about to reach the 15-minute mark. But I think you can see what happens here is that when you substitute in, do your usual 2 pi r, in fact, I'll just do this a little bit. So you do your usual v equals 2 pi r over t, then what you get is 4 pi squared r squared over t squared equals g big M over r. And then let's see, so what this comes out to is that t squared equals 4 pi squared r cubed over big G big M. Right, and then you can take the square root if you want, but that's what it is. And then I guess if you want to do, you can do m equals rho times 4/3 pi r cubed to get the other version. And what the hell, let's see. So actually equals, so the 4's will cancel, and the 3 and a 1 pi will cancel, and then the r cubed will cancel. So actually this is kind of nice. So this comes out to be 3. Is this right? Hang on, let me just do this in Scratch here. So 4 pi squared r cubed over g, and then big M is going to be rho times 4/3 pi r cubed. So switching to orange, the r cubes cancel, one of the pi's cancels, so we get rid of the squared, the 4 cancels, and so this becomes 3 pi over rho times big G. Okay, well, interesting enough. So the answer here is 3 pi over big G times rho. So I think that's I hope it is. Let's see. Well, whatever. Close enough. So there you go. That's your answers for those 2 problems about the planet and its local gravity field, and I will do the last one coming up next.